I said the final step in representation theorem is to prove the continuity of the utility function. Continuity of the utility function means that for any sequence of x to n started from 0 up to infinite, with x is equal to the limit of x to the n when n approach to or converge to infinite, we have limit of ux to the n when n approach to infinite is equal to ux. We have to notice first that continuity of the utility function is a more restrictive property of continuity of preferences. But before talking about this one, let me show you with some graphical representation what is the continuous utility, the continuous function, and what is its difference from other types of like visualization. If you see, there's provided 4 different graphs, and this one, which is the limit of fx when x converge to a is equal to fa, it's continuous at x equal to a. But this function, the fa is not defined. Why? Because when x take the value of a, so we do not have any value for the y. So then fa is not defined. Then the condition for the continuous function is filled here. And also for this function, we can see there is a jump. There is a jump. So it means that fx when x converges to a does not exist because there is a sudden jump. So again, it does not hold the condition of a continuous function. And the fourth one, again, the fx when x approach to a is not equal to fa, because if a take the value, when x take the value of a, we have different value for y than fa. So that's why in this one, and this one, in this 3 graph, the condition of continuity does not hold, but only in the first graph we can satisfy the condition of continuous function, because the limit of fx when x approach to a is equal to f of a. So, but why the continuity of the utility function is more restrictive property of continuity of preferences? Let's talk about this one first. So let's move on. Therefore, we do need to prove the continuity of a specific utility function that we constructed, which is ux is equal to tx. Now consider a sequence of x to the n when n started from 0 to infinite, with x equal to the limit of x to the n when n converges to infinity. So we prove first that the sequence of ux to the n when n started from 0 to infinite has a converging subsequence. By the monotonicity implies that for all epsilon greater than 0, the utility value of ux prime lies in a compact set of t and t, like bar, for every x prime, such that the absolute difference between x prime and x is less than or equal to this epsilon, where the absolute difference between x prime and x denotes the Euclidean distance between x prime and x. So now, since x is equal to the limit of x to the n when n approach to infinity, then there exists an n bar number such that ux to the n, which is included in the compact set, for every n greater than n bar. An infinite sequence that lies in a compact set as a converging subsequence. This is one of the things that we need to understand. Then we prove next that all converging subsequences of x to the m, when m started from 0 to infinite, so m is now as a notation, we want to use m as a, because this is a subsequence of the main sequence of x to the n, or such that the limit of ux to m when m converges to infinite is equal to ux. Assume by way of contradiction that there exists a subsequence of x to the m when m is started from 0 to infinite, such that limit of ux to the m when m approaches to infinite is equal to q but not equal to the ux. Equal to q but not equal to the ux. But we want to finally prove that it's not equal to q but it's equal to ux. So consider first the case that q is greater than ux. Then monotonicity implies that q multiplied by e, because now we are going to change them to a bundle, to a vector, q multiplied by e is strictly preferred than ux multiplied by e. Consider now that p is equal to q plus u of x divided by 2. Then by monotonicity, pe, which is another vector, is greater than, is strictly preferred than ux multiplied by e. Then ux multiplied by e. Why? Because this p is the midpoint of q plus ux. When q is strictly preferred, then ux multiplied, when q multiplied by e is strictly preferred, then ux multiplied by e, then p multiplied by e, which is some value in between or in a midpoint of q plus ux, is also strictly preferred than ux multiplied by e. Then we can say that there exists such number of m hat such that for every m greater than m hat, it's the case that ux to the m is greater than p, and x to the m is indifference to ux to the m multiplied by e, but strictly preferred than pe. See here that x to the m is indifference to ux to the m multiplied by e, but both of them are strictly preferred than p multiplied by e. The continuity of preferences implies that x is at least as good as pe, and from x, which is indifference to ux multiplied by e, which is what we defined in the beginning of this representation theorem, also ux multiplied by e is at least as good as p multiplied by e, is a contradiction of the pe is strongly preferred than ux. Is strongly preferred than ux. Now let's think about here again. When x is indifference to ux multiplied by e, then in this relationship that x is at least as good as p multiplied by e, and instead of x we can use the substitute of that one, which is ux multiplied by e. So now when x is at least as good as p multiplied by e, then ux is also at least as good as p multiplied by e, which is a contradiction for this definition that we have here by strong monotonicity, that p multiplied by e is strictly preferred than ux multiplied by e. Then it means the condition that we define here, which is limit of ux to m approach to infinite is equal to q but not equal to ux, but we find that this contradicts to that one. Then we can say that the ux to the m is equal to the ux, because when we go by that by contradiction, this contradict the definition of the strong monotonicity that implies here. And also the case for when q is less than ux is also symmetric to the same things that we can prove that one also. So now we also proved that the utility function should be continuous. So we proved three things here. The utility function, first of all, we proved the sufficiency condition, and then the necessity condition, and finally we proved that the continuity of the utility function. But we have to notice something here, that there exist preferences that have no utility representation. Think about this one. Consider, for example, the following lexicographic preferences which is the bundle of x1 and x2, is strictly preferred than bundle of y1 and y2. If and only if either x1 is greater than y1, or if x1 is equal to y1, then x2 is greater than y2. This continuity follows from the fact that the upper contour set and the lower contour set are both neither closed or not open. So in this lexicographic preferences, we do not have a utility representation here. So now, consider a weak assumption than a strong monotonicity, which is very strong assumption, which is like local enunciations, but enough for the representation theory. A preference relation, this one, is a locally enunciated if for every x, which is consumption bundle and consumption set, and every epsilon greater than 0, there exists such a bundle of y, which is also in consumption set such that the absolute difference between y and x is less than or equal to this the value of epsilon. Then the y is strictly preferred than x, because here more is better. Again, same as the strong monotonicity. Where the absolute difference between y bundle and x bundle denotes the Euclidean distance between point x and y in an L-dimensional vector space. L-dimensional vector space we can define by this formula, which is the absolute value of y, the absolute difference between y and x is equal to the sum of xl minus yl to the power of 2, or the sum square of this one, which L starts from 1 to the capital L to the power of 1 over 2, which is we define this L-dimensional vector space. From now, we shall assume that a consumer preference relation is continuous, because we proved that one. And the continuous preference is satisfying when the consumer's preferences satisfy a strong monotonicity or local enunciation, then the preference relation can be represented by a continuous utility function. Then the preference relation can be represented by a continuous utility function. So this is what we proved the representation theorem, that we represent preference relation by using utility function. This is the end of utility function and representation theorem. In the next session also, we will continue on talking about consumer theory. We will define some other terminologies within the consumer theory, and then we will move on the utility maximization, which one of the building block for the consumer theory. For now, I hope you enjoyed this lecture, and I would like to ask you to please subscribe my YouTube channel in order to enjoy other videos related to microeconomics, especially in intermediate and also advanced level of microeconomics. Thank you so much for watching. See you in the next video, guys.